To mitigate swelling and scaffold formation in the blast furnace, several strategies can be employed. The first control, the very first is the control the pellet porosity and the basicity. We are talking about a furnace where pellet dominating the iron or that's the ferrous burden. It's important to that use pellet with an optimized porosity, for example, between 27 to 30%, along with the optimal total basicity to minimize swelling during reduction process. Secondly, we have to introduce the additive like MgO that can use to improve the structural integrity of pellet during reduction. And finally, to maintain proper reduction condition, this involves avoiding conditions that could cause abrupt phase transition and which are known to increase swelling. And you should also control the gas composition, specifically the CO-S2 ratio and the temperature to reduce swelling stress. Now coming to our second slide, which is about the monitoring and basicity influence. So regular monitoring is very critical. There is no doubt about it. And you should use the furnace probes and the sensors to detect any early sign of a scaffold formation, so you can act promptly. Now let's discuss how basicity influence swelling behavior. At low basicity below zero point 0.5, swelling is low for pellet of both porosities. Now, this suggests that acidic slag, which have a lower basicity, help to stabilize the structure. At intermediate basicity around zero point 0.8 to 1, a material with 27% porosity shows a sharp increase in swelling. This is likely caused by the formation of unstable oosteite phases or excessive gas generation. So now coming to our next slide, which is about the basicity and the operational relevance. So continuing with the basicity's influence, we can see that at higher basicity above 1.2, which is more than 1, swelling significantly decrease for both porosities. Now this suggests the formation of a stronger, more stable phases like calcium ferrite, and these guaranteed these. Now high basicity also improve the slag fluidity, which helps accommodate volume changes, and this has a significant relevance to the blast furnace operation. So material with a higher porosity and optimal basicity of around 1.2 and plus are preferred because they minimize swelling phenomena. So improved reduction kinetics also help by these, and ensure we have to ensure that better gas permeability within the blast furnace. There is no doubt about it. Now coming to our next slide, which is about the controlling basicity and porosity of the burden material, which are very crucial for maintaining the furnace efficiency and preventing operational disruption. So for material selection based on the data, material with a porosity of about 30% and a basicity about 1.2 are ideal. Now these parameter helps achieve a stable reduction behavior without going over a swelling limit. And let's briefly touch on reduction reaction rates. Flux pellet which contain added fluxes like lime and dolo react faster, and due to their higher porosity and uniform composition. And this additive also reduces slag formation and improve reducibility up to a large extent. Now, coming to the reactivity of different pattern material, comparing different materials, acid pellet have a medium to high rate of reduction. However, they have a lower reducibility compared to flux pellets because they lack added fluxes. So while less reactive than flux pellets, their reaction rate is still higher than that of lump ore. And lump ore has a medium to low rate of reaction. Its variable physical and chemical properties leads to a slower reaction. So we can say that the larger sizes or denser structure of the lumpur hinder gas diffusion, making it the least reactive of these. And as we know that these reduction are basically diffusion oriented. Now coming to the ideal burden composition, the ideal composition of the burden in blast furnace is tailored to balance efficiency, cost and raw material availability. So general guidelines for the composition is around 40-50 flux pellet, and it's always important, and it is the tagline is that the availability, raw material availability, and nothing there is some fixed formula. Now, these ensure high reducibility and provide better softening melting properties. 30 to 40% acid pellet, these provide structural stability and complement the flux pellet. 10 to 20% lump is good enough, and this helps maintain permeability of the burden, but its use should be limited to avoid issues with the slow reaction. And the rationale is that the flux pellet reduce slag volume, which leads to higher productivity and lower coke consumption. And that's why we have to take a very judicious call that what should be the our balance of the burden. Now coming to the acid and flux pellets, these acid pellets are often less costly and provide strength to the burden. Typically, acid pellets have a low basicity with a CO2 SiO2 ratio is less than 1, and as they are made primarily from the iron oxide with a minimal fluxing agent. In contrast, basic pellets have a higher basicity with a CO2 SiO2 ratio typically greater than 1. Because they contain fluxing agent like lime and dolo, the impact of basicity on the reducibility is significant. Basic pellet form low melting point compound such as calcium ferrite and during induration, and this enhances their reducibility. So we have a benefits by incorporating this basic component. Now, chemist, let us talk about on a component of reducibility. The calcium ferrite, the basic pellet promote better reduction kinetics. They are more reactive and reducing gases like CO and S2. So our reduction gets faster if we consider the same volume of the gases. Otherwise, if we have to fix up the reduction rate, then we can say that our CO and S2 will lesser consumed. So which facilitate faster oxygen removal from the iron oxide. In acid pellet like silica forms silicate compound and that are more stable and refractory, and these compound resist reduction, therefore decrease the overall reducibility of the pellet. And we come across the pros and cons of the acid and basic pellets, and and also we have to consider the microstructure and porosity part. So basic pellet typically have a higher porosity, and this is due to fluxing action during the pelletizing and induration process, where fluxes react with impurity creating voids and micro cracks. So this is a good justification why we have got a texture orientation of lime and acid. Now coming to the porosity and softening melting zone, these basically increase the porosity, the increased porosity in the basic pellet, we can say it enhance the gas permeability and it allow reducing gases like CO and S2 to penetrate deeper into pellet and react more effectively with the iron oxide. On the other hand, acid pellet have a lower porosity and they are denser with fewer voids because of their minimal flux content, and these compact structure hinder the gas diffusion, as we have already discussed and sensitized that this is dominating in diffusion based reduction, which slows down the reduction process. And in the softening melting zone of the blast furnace, basic pellet perform better. The flux within them reduces the viscosity of the slag also, which in turn enhance reducibility. And now coming to the some uh, slag viscosity and experimental observation, acid pellet with lack fluxing agent contribute to a higher viscosity slag, and this can hinder reduction kinetics within the blast furnace. Experimental observation from a study using thermogravimetric analysis and reduction experiment confirm these points under identical condition. And basic pellet exhibit faster weight loss, which indicate the faster oxygen removal. It's quite direct relation compared to the acid pellet. And this superior performance is due to the both higher gas diffusion, number one, and greater porosity, number two. And both composite way helps in mitigating or fuel reduction and our this optimization of fuel rate, particularly in the blast furnace.